I wanted to give you some concepts, like I think they are important, so I won't be able to cover everything related to counterfactuals and effect estimation, but I think at least the main topics, in my opinion, this should be part of the course, so that's the plan for this lecture. So I'm going to just introduce the counterfactuals and say a little bit about estimation. The effect estimation, it's a huge topic in causality, although it's currently focused only on the backdoor adjustment. But since there are so many issues, people are kind of working, and I won't cover everything, but I will give you at least the main ideas. But those could be definitely topics for many lectures. So we can, I mean, if you're interested in any, like in the end, I'm going to also list a lot of other topics that I couldn't cover. So if you are interested, I can help you to find, like to give you some pointers, some papers. They are not listed here, so you need to send me an email and then I will provide to you. But I'm happy to do it. It's just that there's so many papers and I don't want you to get a list. Okay, so that's the third layer of the Pearl's causal hierarchy, and it's related to counterfactual distributions and the idea of having this parallel world. So you have a way of combining different realities. So up to now we were focused on imagining that you have the only one scenario where you observed some values, so that's the observational world. However, you take the same world and imagine one intervention, so one or more intervention if the X is a set. But you never imagine combining things from different worlds in the same distribution. And in this case, you can do it, as you will see. So, and all this distribution, so all the three layers of the Pearl causal hierarchy follow or are induced from the SCM. So the SCM is the true nature, like it's the true data generating model, and encapsulates all the information you need. So if you had access to the SCM, you would be able to compute counterfactuals from different reality, from everything. So I won't show you an example, but when you get, for example, the chapter 7 in the causality book, it starts by showing how can you compute the counterfactuals directly from an SCM. And the point is you need the U values, because usually counterfactuals is something more individual. It's something like what would happen if I, as a person, would have taken a medicine but I didn't take it. So it's a different reality. I know, so I did something, so I changed the world, I observed something in a different reality, in this reality, and then I want to know what would happen with me as a person. And the individually, this information, this specificity is in the U values. So basically, the idea is to recover your U variable and then compute it. It's kind of boring. It's, if you have the model, you can get the error terms and then kind of estimate everything. Of course, that's not the goal. So we can compute counterfactuals without the SCM. So the Pearl's causal hierarchy tries to deal with inferences in the three layers without assuming the structural causal model. So we saw, for example, how can we get observational how can we deal with observational queries, and this is just getting observational distributions, right? So we have a representation, a graphical representation of observational quantities, and this is in the causal diagram, right? So the causal diagram, we have here the nature as it is, the factual world. When we move up to the second rung of the ladder, basically we are talking about making interventions, but you don't really it is like the same world. Like you want to know what would happen in that exactly world if I do some action. And basically it's a populational inference. You want to know, like, in general. Of course you can get conditional queries, like what would be the probability of y given do x and some covariates z. So this would be the covariate specific causal effect. But the z works in general. So this is like a populational level inference. And you see that sometimes I use this notation. So this probability of y subscript, this is equivalent. So these two notations work for, they represent just an intervention. So what would be the value of y after doing an intervention on x, right? But there's no conflicts between roles when I write this. Anyways, but I have a graphical representation of interventions, which is the gx bar. So that's the interventional graph, right? So where I remove every incoming arrow into the variable x, which is the intervening variable. So since I'm intervening on it, I'm changing the value. It's a hard intervention. I don't have arrows. So basically I can compute the graphical, I can get the graphical representation of this interventional distribution by just removing this x. When I move to the third rung, things start a little bit, they start to be a little bit more complicated, because as in this query here, I'm asking something that there's like two different roles happening. It's like, what would be the probability of the variable y if I do this intervention, but something happened already. So I already have x, I observed x equals to x prime. So for this group of people that have x equals to x prime, and I observed that their outcome was y equals to y prime, what's the probability of this y in this different road where these people received x equals to x, not x prime? So you are selecting the same people. So basically you want to infer the use of those people and then get kind of what would happen in this different reality. This is not that hard. Let's just go to the next to see a little. And then we have a graphical representation. I don't want you to parse this right now. I'm going to introduce what is this later. But we have a way to, and a difference. So we have the Rubin's framework for potential outcome, the potential outcome framework by Rubin. It started in economics like several years ago, and everything there, it's in terms of counterfactuals. When you want interventional queries like this one, you just write like this. And the difference between this, it's not only notation, so there is actually a semantics involved. In Rubin's framework, yx is not it's not the variable y after an intervention by the function do. It's actually a new random variable, which is called yx. So in the end, it's equivalent. So Pro showed that everything that you can do using the yx as a random variable can be done by using y given do x as pointing like what would happen with the same random variable y after an intervention on x. But Rubin deals with the problem by using yx as a different random variable. So, and so that's one of the, like I would say, philosophical difference. But the language is very powerful. So when you move up to the third rung, you really need this counterfactual language to deal with all these different realities. And the first definition is potential response. So potential response, so that I'm giving you here the references in the book. But the potential response, which is this yx here, is basically the solution of y after evaluating. Remember, we get the model, the SCM, so we have an SCM, and we compute the value of y after removing the line of the x. So we get the model, the submodel mx, where the x is, so here is a set, but if it's not a set, there's only one line. But for every x, you just set to the value of a small x, and then you just evaluate what's the values of y. It's just a solution. But you can kind of see this as a different random variable. So yxu, so it's the y, the value of y after doing the intervention x, but in this same context, which is given by the u variables. And now it's important to know that there is a u variable, so that's why sometimes we have the u here. And although there is the u here, most of the times we just hide it. So, but the u is there. But it's a random variable now. So as I told you, so this is equivalent. So probability of y given to x is the same as probability of y x sub x here. However, we can denote counterfactual quantities relating other realities. So for example, I can write this, right? So probability of y given x, given that I have observed that the x is x prime. So you can ask different things. So this quantity would be the probability of y to an intervention do x equals to x, but only for those individuals who actually had x equals to x prime. So I don't know if you see this as a difference, but as you treat this as a random variable, it's no longer like if you believe that there is just one world, it's not possible to get like x equals to x prime and observe y only you have just where x was x. It's a conflicting thing. And here, usually you won't observe, like in a data set, you won't observe yx for the same person, yx when x is x prime and when x is just x. So sometimes people sees the problem of counterfactuals as a problem of missing data. So because you only observe what happened with a person in one category, and you treat that what would happen if you change the x as a missing value. So sometimes people frames as something like this. And we have, of course, the counterfactual probability. So we saw the observational probability distribution, then we saw the interventional probability distribution. That exists is the counterfactual probability distribution. And it's kind of the same idea, right? So I think I gave you the redefinition of how you compute a distribution. So it comes from a model. And you see here that I can combine really weird stuff, like what's the probability of a variable y when I has received the intervention on x, and the joint with a variable z that was after an intervention on w. So you are combining multiple different things. And basically, this is just what this means is just getting all the people, right? The U's are just people. So all the observations that matched to everything that was asked here. So that's the usual way. So if this was just the observational distribution, you wouldn't have the subscripts. So because it's always the same variables in the same road. But now the only difference is that we have these subscripts because they are now different random variables for different realities, but they are random variables. So this y, x, z, w here, they are solutions for the same variables, but after evaluating different submodels. So you have now the model mx, where you remove the lines for x and you made them constant. But you have another model when you change the w, and then you have another model where you change I don't know what. But then you have solutions for different models. So there are different realities where you had different interventions. And as long as you are talking about the same u variables, you are talking about the same person, the same individual. So you could kind of, if you had the u's, you could kind of get what would happen with the same person in different realities. So that's the idea. So it's even like called imagination or counterfactual is kind of introspection or retrospection, I don't know. But anyways, this is what happened here. Yeah. Okay, questions up to here? It's just philosophical. Okay, so the first thing that we need, so when you deal with counterfactuals, so if you go to the book, there are like several axioms. I won't provide you all the axioms here because it's not our goal to give you the calculus and the algorithms to deal with counterfactuals. I'm just giving you a general idea what this is. But one very important rule, which is it's like a corollary of an axiom, it's called a consistency rule. So it says the following: if a variable x was observed for some u as small x, the value y, after setting x equals to x by an intervention, has to be the same value of y as if you have received the x by in a natural way. So basically, I don't want that. So if a person was observed with x equals to x, and this x was just naturally received, so just by chance you got this x, and you were also for the same u, right? So for the same u, this give you the value y for the value, the small y for the variable y. Doesn't matter if I give you the x by intervention or if you receive the x by chance. The y value has to have the same. The variable y has to have the same value y in the end. So that's the consistency. So in words, if you observe the x for some u equals to x, and naturally your u was y, your yu is equals to y, then forcing x to be x by intervention has to give you the same y. You cannot change. Setting x to a value it already has should produce no change in the world. And so this kind of gives you the following change in the probability. So since this is now a random variable, basically the random variable yx is the same as the random variable y when x is equals to x. So you kind of can change this. It's one of the rules when you do counterfactual calculus. So this is just a note, so you can see, but it's just that the consistency rule, as I said, is a corollary, like it's just a special case of another property that's called composition, where that's actually the real axiom. So you have this w. Basically, it doesn't matter if you have another w. It's like they do calculus when you have the w there, and it's just if you observed x equals to x under some intervention w, you still, and then the y has to have the same y when you don't have the intervention on x. Okay, so now we have the graphical representation of counterfactuals. This was proposed by Balk and Pro in 1994, and it's called twin network. So this was provided just for two realities first, and then it was extended by Spitzer for multiple realities. But let's see the twin networks first. And basically, you combine the actual or observational world with the intervention or with the hypothetical counterfactual world. Let's just go to the example here. So suppose that I have three variables, x, z, and y, and each of them has a u. So the u's are important now. So I'm giving nodes for the u's. You could put bidirected edges, doesn't matter, but I want you to see the u's. Why the u's are important? Because the u's, they should be invariant across all these multiple realities, because you never intervene on the u's, supposedly. I mean, you are imagining interventions on real or in observed variables. So the use should be all the same across all these different realities. So the idea is just to have copies of all graphs in each reality. So for example, this is the observational reality. That is a graph. This is the interventional graph when you have intervention on X. So I have a subscript for every variable that's under the intervention on X. So that's the ZX, then the YX. And the X itself is no longer a variable because it was set to a value X. And the important part is that they are all connected by the U's except the one that had an intervention. So the Z's are connected by the same UZ, and the Y is connected, the two Y's are connected by the UI. Clear? Okay. That's not done. There is a special thing going on later. I'm going there. But the point is, this graph is going to be helpful because you can now check independencies between variables in different roles. So you can, for example, ask what's the independence between YX and X. Actually, so I can in the same row I can check as before. So I can see, for example, that Y is independent of X given Z by this separation. However, YX is also independent of X without conditioning on anything. So if you see, there's no path that's open. And this is kind of, you are not conflict, there's no conflict here. So this is the same as getting Y independent how can I explain this? Like it's kind of saying that the Y and the response of Y given X is not confounded. So thinking in the potential, I believe that's one of the major limitations in the potential outcome framework. So every time that you think about confounding, you don't think about a graph because they don't have graphical visualization there. You always just see independencies and probabilities with random variables with these potential responses. And in this case here, you are saying that receiving some treatment is not confounded with the variable that the response of Y after getting X as an intervention. It's kind of weird to say, but it's the same as saying that the effect of Y on X is unconfounded. It's really hard to see in their language. That's why Pro invented the graphical language of causality. So it's much easier to identify interventional distributions or see effects of interventions through graphs without potential responses and anything. But the potential outcome framework is still like, I don't know, stuck in this type of reasoning. But anyways, you can see, for example, here as well that if you cannot get the effect of X on Y by conditioning on X on Z. This is kind of this is in a proper causal path. So like X and Y are independent given Z in the observational world. But if you get the response of Y given an intervention on X, if you condition on Z, you open this path here. So you cannot get the causal effect of X on Y conditioning on Z in this chain. It's kind of hard to see. And I mean, you don't need to understand in this sense because there is the theory by Pro that allows you to understand the effects of intervention through graphs. And that's another thing. But that's a way. So instead of just looking at the variables and asking, is Y sub X independent of X without seeing the graph, can you kind of see if this is true or not? It's impossible. And that's his point. Yes. So that's the idea. So you can kind of see the implied independencies and dependencies between variables that are in different worlds. And as I said, Spitzer in 2007 with Pro, they generalized the twin networks to multiple worlds. So it's not only sub X and the observational. So we can actually have different copies, one for different realities. So for example, for the same graph, so I have here X, Z, and Y. That's the observational world. So I could have, that's the graph for intervention on X, and that's the graph for interventional on Z. So it's just a chain. So when I have intervention on X, I remove the X, and when I have intervention on Z, I remove the Z, and this edge doesn't exist anymore. However, they are all tied together by the use variable, right? And so this UX is combining those. This is no longer a variable, so the UZs are the UZ puts Z and ZX together, and so on. The UYs are, and the Ys are all together because of this UI. And you can again check like independencies. So those are the three from before, but you can now, for example, get this. What's the independence? Is YX dependent or independent of X given YZ, ZX, and Y? It's kind of hard to interpret this thing, but basically you see that there's no independence. So if you try to get the effect of Y on Z and the Z on Y and the value of Y, so you observed all these three variables, you create a dependence between the response of Y given the intervention of X and X.
Wouldn't it suffice to just a totally different example, but again to condition on Z, so just Z, because Z is a collider and Y, X is...
This Z?
Yes.
You want to see which dependence or independence?
Yeah, I was just asking for myself to see whether
you don't want a condition on colliders. Because
yeah, I know. So it would be dependent, Yx would be dependent of X given Z.
Yeah, so for example, Yx is independent of X marginally.
Yeah.
You don't need to condition on anything. But
oh wait, it even says, that was a stupid question because my question basically was on the board. I oversaw that, sorry.
Yeah, no, basically what I'm trying to say is that you can get dependencies and independencies between anything you want. Like the goal here is not to see causal effect. But yes, the meaning of the variables kind of, I don't know why someone would like get the effect, the value that you got after an intervention on Z, and the value of Z after an intervention on X, and then the Y, and then the observations of all of these and see, given those, if the response of Y is dependent. I don't know why someone would like something like this. But the point is, if you just look at this, you have no idea of what's going on. But if you look at the graph, you understand why they are, if and not they are dependent, and maybe why, right? So it's giving an explanation and a way to test. That's the most important part. Is a way to test independencies among counterfactuals. That is a note that's very important. That's in that graph, when you have copies of these multiple worlds, some nodes sometimes are exactly the same variables because you don't change their parents, or they are tied together by the same use variables and the parents. So in the end, they are going to assume the same values. The domain of these variables are going to be the same. So it is just a copy, and you don't want to condition on same variables. You give like wrong values. So this is an example. So that's kind of so suppose that you have X, Z, and Y, and that's the actual world, so the observational world. You have this bidirected edge between these two. So you see here that X and Y, the effect of X on Y, is computable by backdoor, right? By conditioning on Z, you block the backdoor paths, so I would be able to get the effect of X on Y. Anyways, this is just a note, but the point is, if I want to construct the twin network for it, considering an intervention on X, first I replicate everything. So Y is just a value, is no longer a variable, but then I have a Y x tied with the y. So I'm not using the u's, but by directed edge means a u variable here. So they are tied together. And the point is, like, there is a u here, the ux pointing to uz. And I would have to create like this bidirected path, bidirected edge, because the ux of this has to point to the other z, right? And it's two z's as well. And anyways, it's a weird graph because it's just a copy of these two data sets, the two variables. However, if you see these two z's, they have the same parents, because the u, this z here receives the u of here and the u of here, and the other z receives the u of here, which is this u here, and also the same u here. So if you were able to see the support, right? So what are the values of every of these two variables? They are identical. They are exactly the same. And the point is, I cannot leave this graph as it is, because I would, for example, have weird stuff. So for example, y sub x would be dependent of x given z, but independent given z and zx. But z and zx are the same. So instead of doing this, actually you have to reduce the graph, putting all variables that are the same together. So that is these two lemmas I want you to read if you are interested, to know the procedure, but it's very intuitive. It's just about merging these variables and then keeping consistency. So the z points to both y now, right? And the bidirected edge is just here. You don't need to tie the z's, they are the same already. So this is actually the counterfactual graph for the graph between x, z, and y. So there's only yx left.
Is there a reason to, I mean, I guess probably the lemma, the small x that points into y of x?
Why?
On the left graph, the small x that's basically set for, we're changing this to x, y,
yeah, you could add the x as well.
Okay.
Yes, you could x. I mean, it's just, yes, you are right. So you would be able, you would have the y, the x pointing to yx here. But then you can use this graph to get the correct dependencies and independencies through the separation. So yx is independent of x given z. That's the correct answer. So you wouldn't be able to see here, because you would need to condition on both to block all these paths, but they are the same. So once you condition on one, you condition on both at the same time. So you need to make this transformation, and now you are able to test counterfactual quantities in a correct way, right? So that these equalities are constraints they have to be dealt with. Okay. And why this is interesting? Because that's just a backdoor graph, right? So this x, y, and z is a backdoor graph. And there is this theorem, that's the theorem 431 in the prime book by Pearl, that says the following, that if z satisfies the backdoor criterion, then it holds always that yx is independent of x given z. That's the graph we just saw. So that's the backdoor graph. If we I mean, it's just one example, but the point is the theorem is saying that every time that the backdoor criterion is satisfied by a set z, you will have this condition here being true, that the yx is going to be independent of x given the z. And I don't know if I wrote here. Yes, I wrote here. And in the potential outcome framework, no one shows this. They just say assumption. There is an assumption that the yx is independent of x given z. And if this holds, which is called conditional equalability, sometimes they call it conditional exchangeability, sometimes they call it conditional confoundance. So there are different names for the same thing, just to guarantee that the y sub x is independent of x given z. And there are a lot of papers explaining how can you get this set of z to make this work. And but a lot of people just write papers saying, as a common assumption in the field, we assume that this is holding for some set z that you just believe that's doing it. And sometimes people just get the whole data set and just assume that's just satisfying this because there's no other way, because this is what people do, and that's not the case. So you can
just not know about it, or are they lazy, or?
I think so more and more I've seen people writing papers explaining this, but I think they don't know the full thing. So for example, they don't know that you can, most of the times they say, oh, if you have the information to create the causal diagram, you don't need this. You can learn a PEG and do from a PEG. So they don't know this part. So you find like several mistakes in their papers, saying that I've seen since people saying this is a usual assumption because it's untestable. I actually read this already. To something like you need a lot of information that you don't usually need in a large system, because, and then, or sometimes I don't know, people are just making excuses because I don't know. I think in the beginning, where way before, because as I said, the potential outcome framework has like 50 years. So from before, you didn't have graphs. You were only working with this language. And they proved a lot of stuff saying, oh, look, if I find this independence, I can do a lot of stuff. I can prove theorems assuming this. And they moved forward, but they never understood why this was true. And then Pro showed that this is nothing as the blocking the backdoor paths, but it's like a lot of big names fighting. And Pro is not actually very, he's also a difficult person, and maybe you are following him in the Twitter. So instead of, I mean, all the texts that I read in the internet, like about this, Pro is always saying, I'm not against your framework, I'm just providing something to support something, or giving more transparency for your framework. But then people in the other side say, no, there is a paper by Imbens. So Imbens got the Nobel Prize in econometers for causality, and he wrote like a sixth page paper saying that the Pro's framework is only philosophical and it only works for toy models. It is completely untrue, and saying that you can never run causality with 100 variables. That's not true at all. Like you don't even need to work with the 100. You have the projection, get the 5 variables, 3 variables, whatever, and just see if you have. Anyways, and I think people just read the Book of Why, and the Book of Why there's nothing about causal discovery, and they just assume that that's the whole theory, which is not. He wrote just for dissemination, and I think people are not willing to learn something new, and they are just finding excuse. But I've seen more and more papers trying to connect and saying, see, this holds if you have the backdoor adjustment, but it's not all of them. Like you find like papers, I don't know. There are a lot of applications of causality in this framework, just assuming without testing. There are many. So just be careful. And now you are an expert in causality, so you can kind of read very carefully every time that you have it. So we cannot dismiss anything that they are doing, because everything that they are doing is still important, but the point is you have to test if you want to have a reliable conclusion. So that theorem is it's connecting both, so you don't need to assume, you just need to satisfy the backdoor criteria. And there is a nice way to see if the condition that they are asking about is true or not in any graph you have. Here is a derivation. So for the backdoor adjustment, using counterfactual language. I think it's interesting to see. So it's just a very simple example of how you operate with counterfactuals instead of working with do calculus and as we were doing before. So if I want the effect of x on y, I want this quantity. I want to know what's the response of y on an intervention on x. So this is a random variable, right? So it's not an operation, it's not a do operation anymore, it's just a random variable. So we can do probability, use probability properties as before. So we can sum over a set z here. And this is just conditioning on z, probability of z. Okay. Then in the second line here, I use the property that the yx is independent of x given z. Because of this, you can, so no one came, right?
It's not, yeah.
Yeah. So because of this, I can add x. Right? So x is independent of yx given z. So from this probability to this probability, I'm using this independence. I'm adding the x. And now I use the consistency rule because every time that I observe x, I have the observational y equals to the interventional y. Got it? And then you have the same expression as before. So this is an easy derivation because you just need consistency rule. To operate over counterfactuals, you have more axioms. You have a list of 10 of them. In reality, you have like 2 rules plus the axioms. But this is out of the scope. So, but you could operate and get the same results just without graphs by just, and you see here that here I put that by theorem, but in the beginning they didn't use the theorem. They used that this independence holds by assumption. So that's why they derived the same thing, but using an assumption here. But you don't need to use as assumption. You just can verify and then use the theorem and then you get the result again.
And I guess in case that it doesn't hold,
then
you can't do it.
The backdoor doesn't work. And if you do it, you're just computing stuff. There's no meaning, right? But people are just calling causal inference.
I mean, I guess there's easy software available to test that.
Yeah, there are huge. So this is going to touch a little bit about estimation, but they are working on estimating the backdoor estimate, which is this expression, for 50 years. So the literature is huge. So they are combining regression, matching procedures, like working on tricks to avoid instability of some weights, because you can have like his weights very close to 0, very close to 1. You can combine with deep learning, you can combine with machine learning, you can combine everything together. But that's just estimation. It's no longer causality. Like once you know that you want to estimate the probability of y given to x, it's just a condition independence. So, but they are working on this for years, and they're packaged in R, packaged in Python. There's packets everywhere. There are books written for like causal inference for statisticians. They're just work on the potential outcome framework, and the first chapter is like, let's assume this, and now it's only estimation. I don't see this as causal inference. I see this as estimation of the backdoor estimate. But unfortunately, like, and it's not a problem of the potential outcome framework. The potential outcome framework starts as a very general framework, putting everything in terms of counterfactuals and potential response. But they only know how to operate under the assumption that y sub x is dependent of x given z, and then do stuff for this. And in the end, like, people that are applying are just focused on this particular case. Anyways, but that's what it is. Okay, so I want now to move to estimation of the adjustment formula. So doesn't matter. So I put here parent because I've seen some presentations where people were just estimating the backdoor formula. And again, I'm not giving names here, but it's really funny because they say, oh, you don't really know if the if the set Z is a good one. So they're like papers and papers about how to select the set Z. And sometimes they come with these parents. So if you know all the parents, oh, that's a good. If Z contains all the parents, that's a good set. But yeah, that's true. I can draw. You can draw the graph, right? So you can put like all the parents as known. So you have X here, and all the parents are known. So all the variables here, they don't have bidirected edges because the parents are known. So you can have like bidirected edges everywhere, but as long all the parents are observed, you are going to block by conditioning on the parents. And of course, this satisfies the backdoor adjustment. It was one of the criteria I gave you, like in the very beginning, there was like parent adjustment. Because of this, it's one of the selection of the covariate sets. It's funny, but it's here. But you don't even need to use just backdoor. There's the generalized adjustment criterion where you can use descendants, right? So the generalized adjustment criterion that I gave to you that works even for pegs, it allows you to use even descendants of X as long as it's not blocking the proper causal path. So we had this before. And as long as in the end the effect has this form, you can use it. So you don't need to get backdoor. You can have generalized adjustment. Anyways, so the focus is to estimate this, right? And in principle, if we have consistent estimators for these two guys here, so I have like this estimation, I have this estimator and this estimator, and there are like a huge literature about how can you do either non-parametric or parametric dense estimation. So you can use from like simple things as kernel estimation to deep learning. I don't know. There are a bunch of things. As long as you have a way to estimate this, you could just apply. What would be the limitation here? Can you see what would be the problem? Suppose that I have these two pieces. It's not just the product, right? So I mean,
you're summing over.
I'm summing over Z, and if Z is like huge or continuous, this is an integral. So it is complicated. It's not a easy problem to estimate this if you consider like a general problem of. And usually, since you are not working on backdoor adjustment with like over a few variables, some people have like, for example, that is this paper that's really famous that's called large scale propensity score, where the set Z is like 100,000 variables because they believe that if you have all the variables in the world, you're going to block all the backdoor adjustment, all the backdoor path. But that's not true at all, right? Because you're just increasing the chance of getting a bidirected path, and just conditioning on them is worth than actually condition just one, right?
So they might just include colliders.
Yeah, they don't care at all. I don't know why. Yes, but we were here. So in principle, it would be easy to get just a estimator of this and just compute this. But the first limitation is that one, like this Z can be high dimensional. But anyways, we would be able to get this. In reality, we don't really work with the probability itself. We want to have some measure of this distribution, right? Unless you are working with Bayesian inference, in Bayesian inference, you actually work with the whole distribution. But most of the time, people are kind of interested in the average causal effect or the expectation of this distribution. So the first step is converting or computing actually the expectation of this distribution. So you can see here how can you compute it. I derive it for you, but basically is applying the definition. So you sum over y, multiply by y, and that's the probability that we have. and we computed, this is only for backdoor, right? So we computed the probability of y using the backdoor adjustment. Then we can, so even for continuous variables, this change of the sums, they work by Fubini theorem, if you know probability. But anyways, you can change the order of the sums here. And then the y, together with this probability of y given x and z, if you remember, this is exactly the definition of conditional expectation, right? And you can convert this within the parentheses to the expectation of y given x and z. So the expectation of y given x and z is just the y and the probability change, right? So you have this. So, and again, if you see this expectation, there is another property of expectations where if this is a function, you just need the probability of the arguments of the function. And this is actually a function of z, because x is constant, because it comes from here. So the expectation of y given x and z is a function of z. And there is another, I think that's actually a theorem, that the expectation of a function is the, right? You know this? So the expectation of a function, of a variable, is just, you can put the integral or the sum, but you can get the function here, but you don't need the probability of the function. You can get just the probability of the arguments, right? That's so that's what we are using here. So in the end, that's just the expectation over z, because that's we are summing over z of this function, which is the expectation of y given x and z. So in the end, it's just two expectations. So you can use the law of the large numbers. I think that's this I don't know if it, no, anyways, but the first thing that you can do to do this, so now that's the goal. We have, we are going back a little bit here. So instead of getting the expectation, we are considering with the probability. And the first approach that you can do is called a stratification. So if z is categorical and has low dimensional, and also this is important. So for every configuration of z, so z is like you are going to stratify your data set into all possible values of z. So if this is high dimensional, you will be able to, it's really probable that you won't observe any observation in this category. So this is an assumption called positivity. You have to have observations for all subclasses that you are considering. So if you have this true, then you can just use this stratification. So you can compute, for example, so this is just sample estimation. So this is the mean, the sample mean estimator. Basically, I'm getting all the y's, so that's the indicator function. So all the y's such that the x is equals to x and the z, so that's assuming that I have a sample. So this is I for a sample. So y, x, y, and zi are my samples. And I just get the values of, so I just get the values of y for those that have x, y equals to my x, and the z, y in this category. So for you, I'm getting, this is the conditional expectation for a specific z. So it's just a stratification. So I just consider the samples where I have the x equals to x and the z equals to z, and then I sum over all the y's. So that's just a way to compute, right? It's a conditional, the sample estimator for the conditional expectation. And the PZ can be computed by just counting as well. So you just get all the z's in your sample that are in this category and divide by the total samples, the total number of samples, and then you get the probability of z. So this works because z is categorical, low dimensional, and everything. And then the expectation of y given to x is you can estimate this easily by counting, basically. So that's what it's doing. However, there are better ways, especially because if you don't have z always categorical and low dimensional, right? So that's a problem. So if z has high dimension, and then enumerating all these possible values and summing over is going to be very demanding. So what we can do is actually use the law of large numbers and use the fact that we have there are two expectations there. So what's written here is like for any f, as long as it's well behaved, we can get this as being true. So this is actually an expectation of a function of z. So for every f, so f of z here, as long as this is well behaved, the expectation of fz can be estimated by just computing the value of the f for several zi's. So I have a large sample with z's and just evaluate the function in all these samples, in all these zi's, and then take the average of all of them, right? So this is just computing the expectation of this function. And so basically, since we have this probability as oh no, I mean this is just two examples. So for example, I can consider the function of z as being just the probability. This is just a function. I can also consider the function of z as just the expectation. So those are just functions. So as long as I can estimate the functions and can be used, and we can estimate these functions through like expectation, you can estimate through regression, right? So expectation can be through regression, through if y is binary or categorical, you can use classification, so you can use machine learning for this. Otherwise, you can use non-parametric methods for regression as well, or even deep learning methods for regression. But you have ways to estimate y for even high dimensional z's. And as long as you have this estimator, so this works because of the law of the large numbers, I can just compute this function for a large number of samples where it's varying z. And this is going to be expectation over z. This is just a sample estimator for the expectation of this function over z, what's written here. And so that's what we are doing here, because expectation of y given to x is expectation over z of the expectation of y given x and z. So what we can do is we can get rid of the fact that we would need to estimate pz. So we don't need to estimate pz anymore. We just need to get this expectation, and using our own sample, we can do the following. So first, we obtain a regression or machine learning estimator of this expectation, and this everyone here can do it. And the second part is like to get the predicted value of y for every z in our sample, right? So we use our sample to estimate this, then we evaluate our function for every zi. So this is going to give us the y hat, the predicted value of the y's. But in the end, we need the expectation over z of all of these values. So we take the average of all the y hats. And this gives you already the expectation of 2x. That's done.
And we fix x to a specific value.
Right, so
That's what we do.
yeah, so
there's no,
if x is like, most of the time as well, like these packets are only available for binary treatment. So most of the techniques are focused on X being binary. They kind of extended for multi-category variables. So instead of having 2 values, you can have like multiple categories. And very few methods allow you to have X continuous. So this is still ongoing. But in reality, you can categorize X into several values and then replicate this for all the X's that you are interested in. Maybe interpolate a function of the expectation of Y given to X for every X that you are interested. If you believe that. But if it is like it's a treatment, then basically you are interested to know if a drug is an effect in comparison to a placebo. So this is 0 and 1, so it's a binary treatment. So you just need to compute what's the effect under the placebo and the effect under Y, and the 1, and X equals to 1, which is the treatment, and then get, I think that's what's actually going to be later. This is called then the average treatment effect. So when you have just the expectation of Y given to X, you are kind of just consider the average causal effect. But when you have a binary, they call it average treatment effect because then it computes the difference. I think that's what's going to be here exactly. So in the particular case in which X is a binary treatment, they compute the difference of the expectation of Y given do X1 and the expectation of Y given do X equals to 0. And in the literature, this difference is called average treatment effect because it's the effect in comparison to a placebo, something like this. If you have like multiple categories, you can get like the pairwise differences until you get, because you have an effect as long as this has a difference for any category, right? So imagine that you have like three different drugs, and you want to compare which drug is the best. So if all of them have the same effect, no one is the best, but you have a difference. So if the one and the second are the same, but the third is different from them, then you get a winner. So you can do the pairwise differences and just get the best. This is what people are usually interested in, to get the best, the one that has the best causal effect, or to optimize a decision, for example, which intervention I would do to maximize, for example, my income or my anyways, something like this. So you want always to optimize, and this means to get the one that gets the highest effect, right? So you can just compute different in comparison to a placebo or to a control or something like this. So in the case of a difference, right? So for a binary treatment, it's the same idea. So you apply the procedure for X equals to 0, then you apply the same procedure for X equals to 1, and you evaluate now for the same ZIs. So you see, you get the prediction for those. So it's the same ZI, and you just apply the function as X equals to 1 and then as X equals to 0. So it's an estimation. And you see here that you are not predicting only those that are in the sample. So you have like observations that were observed with one particular ZI and 1 and other particulars in the same ZI and 0, and
the actual XI for your actual observation is 0 or 1, but
right.
You're using it as an input for both.
Right, exactly. So you are kind of getting a new value for every observation, right? And then comparing these differences.
How dimensional Z in this case? It could be arbitrary or what?
What?
Large Z.
A large Z. So
high dimensional, or what situation are we in?
So the Z here can be high dimensional as long as these estimations are computable, for example, through machine learning, right? So the only limitation in this case is that the X
Binary.
yeah, so for the difference is binary, and you're not treating x as actually continuous. So in this case here, so this stratification assumes low dimensional. But here with expectation through regression or machine learning models, you can have z high dimensional. Yes. So suppose that you still have to evaluate. So these estimations here depends on you having a representative sample for every axis and every z that you are interested in. So if, for example, this is a continuous variable and you have a bunch of individuals for like, I don't know, you have like between 0 and 10, and most of them are within the between 0 and 1, and you have like sparsity in the big numbers. I mean, you have problems with sparsity. So I mean, you have several issues because you are still dealing. So this is all statistical problems that you know already, like with missing data, problems with so the support as well. So for example, if here we are comparing for binary we are comparing under 0 and under 1. So suppose that under 0 I have a good representative, so my sample represents well individuals for this zy, but not for x equals to 1. So you would be, this difference can be really tricky because you have like an instability estimating this function, but not this one. I mean, all these issues with statistics, they are going to happen here. And I'm just touching the surface of this literature here. So there are like in the end, I'm going to just show several procedures that exist, but in the end, people combines like regression with matching, with propensity score, with a lot of things. They try all different machine learning methods. For example, that is a framework called I don't know. That is the X learner, the T learner, the C learner. Basically, they try out all the machine learning methods available and then check if the results are the same to check for stability. Anyways, people are kind of crazy with this, but in the end, it's just estimating regression, right? There's nothing here. But the high dimensionality, it's easily solved by getting machine learning models. I think the problem here would be more about the support, like if you have actually representation for every in every category of z, you have for both 0 and 1, x0 and x1. Okay, so now we have another type of procedure that's called matching procedure, which is not using regression. So the problem is still the same. So here, what did I do here? Okay, so I'm just copying here. So this is from before. So this procedure can, so we just saw here a procedure that uses regression for each of these functions. But imagine that instead of getting regression, I want actually to find individuals that actually have this particular zi, and I want to match all those that has received the treatment and those that didn't receive the treatment. I want to observe like people with the same configuration of z and then match them. Why that? Because this issue of the support that I told you, sometimes you have like sparsity in the data set, and it's good to focus on only these units where you have like a good representation across these z's. So instead of employing regression, we could consider this matching. So imagine that you have like a way to identify all the units that have z equals to z, and then among this, you compare the mean. So it's just like comparison between the y's in this group that has x equals to 1, the treated group, and the y's equals to in the control group. So you first stratify over only the pairs of individuals that have exactly the same z's, and then you compare the means, right? So what do you think? Would this be consistent and a biased estimator or not?
You potentially leave out big parts of the samples you have.
Yeah, that's a big limitation. It's but this doesn't change the. It doesn't make it doesn't make it biased. You get only you lose statistical power, but it doesn't change. So being unbiased means that the result is going to be centered on the true value, and consistent is that once you increase your sample, you're going to reduce this variability, and then you're going to convert to the true value. So it is still okay. So the answer here is going to be true. However, that's the question. So okay, it's unbiased and consistent, but what are the limitations? This is exactly the major one. You are going to lose a lot of people, especially because if Z is high dimensional, it's really hard to match these individuals. And imagine if it's Z contains continuous variables. It's impossible then.
Yeah, well then you'd basically try to discretize it in some manner.
Yes.
Make intervals.
Exactly.
And buckets.
So this is what people are doing, and that's basically what they want. The idea is, instead of getting a high dimensional Z, let's try to find a score which is a function of Z. you're laughing, and you see, it's so. I really like that you're laughing because I'm reinventing the wheel, right? This is statistics. I'm kind of but anyways, we can leverage. We have like 100, 200 years of expertise in statistics. Everything that we learned for estimating distributions we can apply here, and this is what people are working under just to estimate the backdoor estimate. But anyways, this is what there exists there. So a lot of packages they are called causal inference packages, and it's huge. You don't imagine how popular these matching procedures are, and they are just based on the assumption that your set Z is satisfying the ignorability assumption or the backdoor adjustment, and then they are just focused on dealing with these issues with the data. So, but that's actually a clever idea. So basically, instead of working with the Z high dimension, let's find a score that's one dimensional. And as long, now I have this assumption now, another assumption, that X is independent of Z given S. So the S is my score. So as long as basically what I'm saying here is that the treatment is independent of all my covariates given this score that represents all the information that the Z could give me. Let me go directly to the graph. So basically that's so in the graph you can see here, that's a graphical representation of this independence. Basically I want a score that's going to mediate this. So if my Z already blocks all my backdoor paths, I basically can get this S as a function of S, a function of Z, and it's going to block this path. That's what I want, that the X is independent of Z given this function. And in the end, instead of conditioning on Z, I'm going to condition on S because it's still going to work to block my backdoor adjustment. So that's the proof. You can follow, I think there's a bit of time. So it's kind of easy. So basically, I started summing over Z, so that's the backdoor adjustment. So I added this S here, right, but just adding S here. I'm not doing anything here. But then I open up this joint distribution. And now because of this independence, I include the X in this term. Then in the first term now is the fact that right, so basically Z and S are the same variable. So basically conditioning on the S is equivalent to condition on Z. So basically you can add here the S. And with this, I can now, what I'm doing here is, oh, right, so these two terms together, now it's just the joint of Y and Z, right? So that's just the joint together. And I'm summing over Z, so I can remove the Z and then get just the intervention, just get the adjustment over S. So there are two things here that are important. The first one is the independence that I said that it's kind of a requirement to create this score. And the second is one that says that Y is independent of S given X and Z. So basically it's kind of right here without leaking any information. So it's really important that this S captures all the information so that this independence also holds. So this is like independence of Y and S given X and Z. Okay, so now they have this idea of reducing this whole set Z into this S, which is one-dimensional. And if Z satisfies the backdoor, then the S is going to satisfy as well. And now we have to choose which function is going to be. And if X is binary, it's easy actually to prove that if S is exactly the propensity of receiving the treatment given this set of covariates, so that's why it's called propensity score, is the probability of receiving the treatment given that you have a set of covariates. So it's your propensity to receive the treatment. So if you actually compute the function as being the probability, so this is going to be a real value between S0 and 1, and we just need to condition on this one-dimensional variable now. And actually, if you choose S as this function, you have this. So it's not hard to prove. So you can prove this. So in practice, S is estimated, for example, using logistical regression, if you may, I don't know. But of course, if Z is really high dimensional, you can use classification approach for using machine learning. It's just classifying if you receive or didn't receive the treatment, giving a billion of variables. Deep learning deal with this easily. So you could just, as long as if you have a good estimator for this, and if you believe that this is true, then it's fine. There are issues. So there are a lot of people complaining that in the end you apply this matching and you don't have a balancing. You understand this balancing in the end, but since the literature is kind of fuzzy, you don't really know if the people are using the correct Z, because if the Z from the beginning don't satisfy the backdoor adjustment, you won't find balance or even like you won't get the correct answer in the end. So everything here is assuming that Z is a good set, and then everything follows from it. So if in the end you don't get the correct answer, I don't know if you can blame the function of Z or if it is your choice of Z anyways. But people are kind of complaining that there are several issues with this as well. So basically you just rephrase the adjustment. So that's just a cop again. So instead of adjusting over Z and computing the difference, we are going to adjust over S and compute the difference. So S is one-dimensional, so it's much easier to match now. And you can match by using nearest neighbor matching or subclassification. So now you have the propensity score distribution. You can kind of compute the quantiles of this distribution and discretize it, and then see the people that are in the same quantiles. That is actually one method that's called full matching. That's this guy here that you basically automatically finds the optimal number of classes to categorize the propensity score. So that's a paper. I found it interesting. Yeah, so basically the limitation of matching is to lose some of the units that are never matched. So you can have like several outliers, but you have like these several strategies that allow you to maximize the use of the units in some sense. But you see here that it is still sensitive to the choice of the method to find these clusters, and anyway, several heuristics involved. Another interesting use of this propensity score is to use the scores to weigh the observations. So basically, the score is the probability of X given Z, right? So that's the propensity score. And you can actually see how it enters in the distribution. So probability of Y given to X is given by this because of backdoor. And if you would just multiply by this fraction, which is just 1, you are not changing it. And that actually is good because in the numerator, you complete the factorization of the observational joint distribution, and you get in the numerator the joint distribution here. And in the denominator, you have just the propensity score. So as before, you can compute this probability of X given Z, and now it's called generalized propensity score because it's not X equals to 1 or 0, it's for any, but anyways. But they call it as generalized propensity score, and because it's generalized to not only binary variables, but for categorical and continuous. And instead of using logistical regression, you can use now multinomial regression, or instead of binary classification, you can have multi-categorical classification. If X is continuous, you can use regression techniques and so on. But as long as you can deal with this, so you are shifting the high dimensional issue to the estimation of the propensity score. But as long as you get a really good estimation of these probabilities of X given Z, it's you can kind of create a pseudo experimental sample. That's what we are going to see here. So because you see that this probability of Y given Z, which is the interventional or experimental distribution, it's nothing as reweighting the joint distribution with some weights. So you see that's the joint, and if I give this weight for every unit in my sample, I'm reweighting all the samples in a way that it becomes as if it was collected in an experimental study. So I have here an illustration. So suppose that's my data generating model, so my graph here, and in the observational scenario, we have actually that X depends, so the assignment of the treatment depends on the set of covariates. So it's not independent. So probability of X given Z, it's different than just the probability of X because of these connections here. But if I do this reweighting of I multiply every unit in my sample by 1 over probability of X given Z, I will actually remove or minimize the influence of the Z's on X. And then in the end, you will have the independence between X and Z. So suppose, just an example here. So suppose that that's my original sample, and the colors, they represent the Z's, the categories. So suppose that I have just 2 categories, and the Z's that are blue you see that there is an imbalanced sample, in the sense that in the group that's in the control group, I have just 3 samples, and in the treatment group I have 4 samples. And also, if you compute within each category, you see that the probabilities are very different. So for example, the blues ones, they have a higher probability or propensity of receiving the treatment than the green ones. And here I just computed what's the probability of X given Z. So for example, in given Z blue, that's just 1/4. and this given z green, that's 2/3 and 3/4 and 1/3. And that's just 1 over this value, so that's just a number. And and then if I reweight, what I'm doing actually is multiplying the unit. So for example, this unit, it's not going to appear just 1 time, it's going to appear 4 times. Now this 2, because I'm multiplying by this number here, so this 2 multiplied by 1.5 is going to be 3. These 3 units multiplied by 1.33, it's going to be 4. And I could multiply by this, and this multiplied by 3 is going to be 3. And then if you compute here, the probabilities are the same. So the probability, it's always half for everything. So you convert an imbalanced sample to a balanced sample. And when I said, oh, it's balancing, it's not balanced, this is what people are looking for in the end. So that's kind of a sensitivity analysis, or like you can kind of check for several sets z, which z is making the sample more balanced. So sometimes they kind of select the set of covariates z by checking which set makes the sample more balanced. It's kind of a heuristics, but basically that's what they are doing here. With this, basically we get an estimator, which is this one. So that's the answer. I'm going to show you the proof, or not, I don't know, but I think there's time. The expectation, as we transformed the sample as if it is causal, as if it's experimental, it's nothing as selecting the y's that received the x equals to x. So that's the indicator function. So I just get all the y's such that the x is equals to this x here. So, and just I sum them, but the y's are kind of weighted by this propensity score. So for every y, for every sample I compute what's the propensity of that unit given the I compute the probability of so I check what's the value of x for this unit. So what's the probability of x being equals to xi given z being equal to exactly whatever is the z of this unit. And then in the end, I'm basically just selecting the y's that are matching with my treatment. It's intuitive because since I transformed my sample into a causal one, into interventional one, is imagine that if I had this data coming from an experimental study, I don't need to balance, I don't need to do anything, it's already done. So it's basically computing the conditional expectation of y given x. That's just the sample, and the transformation is in this weight here. So that's the mean of all values that are, but they are inversely weighted according to the propensity score. And if I want the average treatment effect, which is the difference in the binary case, I can just compute individually. So I can get here, instead of x, y equals to x, my x is 1 in your case, it's 0 in another case. So here again, I just get the probability of x being to 1 because all of x's here are equal to 1 and all my x's here are equals to 0. And then I just compute this difference. Let's see if I have. So before going to the proof here, I want to ask you, what are the limitations of this approach? If you can see it. So there's no matching now. I'm just getting the sample as it is, converting it to something that we call pseudo-experimental or pseudo-interventional sample, and just getting the sample estimator, the sample mean estimator for the y's after reweighting the samples.
If we were to go back to the previous slide, I mean, we have only one, we give a very large weight to, for instance, of weight 4 to only one observation. So
Yeah, I was gonna say outliers could potentially
Yeah.
skew the.
Yeah,
We give them a lot of importance.
yeah, so you have a problem of sparsity. So the z, so we still have the issue of the so to compute this probability of x given z, it's not just putting on the deep learning approach and getting it done. So for example, if the z, one category of z is not representative in the sample, you may get like a very low score for the probability just because you don't have units. And so these scores can be very close to zero, and then when you invert it, you have like a very instability in the estimation. And this is not because the individual got a z or a set of covariates that's really rare. It's just because you didn't sample enough to get this. I mean, it's rare, but not that rare as you are seeing the sample, because the sample can be just small and you were unlucky or something like this. So you will have several issues related to instability because of these weights. So they have extensions. So they have the augmented inverse probability weighting. You have a new way to, like, instead of getting one here, you get some weights to help with this instability. I mean, you have several generalizations to kind of deal with this stuff. But this is a very famous method, inverse probability weighting. Right. And I don't know if you are interested or not, but I got a proof here. Actually, I couldn't find this proof anywhere because most of the times the proof is in terms of counterfactuals, because it comes from the counterfactual literature, and I would like to provide you a proof following just the probabilities, the deuce, right? So under the interventional distribution. So it's not that hard, but I don't know, maybe it's not that intuitive. So basically we can compute this by, so the first part here is just applying the definition of expectation, and the probability now has the weights, right? So we have here in red the difference between the backdoor, the usual backdoor, and the weights. So we just put them together here, so I'm not doing anything crazy in the first line. But then I'm putting now in terms of expectation. So first, this part becomes expectation of y given x and z. You saw this already. And the part out of the brackets is just the expectation of this function over z. So that's the expectation over z. So this is fine. Now there is this part where I don't know if you saw this already, but that's called fundamental bridge. So it's just a way to, instead of using probabilities is nothing as the expectation of an indicator function. So that's called fundamental bridge. So if I want to compute the conditional probability of x given z, is just getting the expectation of this function, where I only get 1 if x is equals to x and 0 otherwise. So basically I'm just getting the expectation of the counting, right? So it's the same thing. So this is true. So what I'm doing in the numerator is replacing this probability with the expectation of the indicator function. Here was small, here is big, but I mean, it should be z equals to z small. And then here is an important part, that basically it uses the fact that, so from this is what I have here, so it's just copying here. So from here to here, what's happening is that this indicator function is independent of x given z, because it's basically, I'm already selecting, not independent, but I'm already selecting. So this is going to be 1 only when x is equals to x. So conditioning on x is true all the time. So I can condition on x. And once I condition on x, I have this independence between y and the indicator function given x and z. If you don't see this automatically, you can use the graph. So basically, So basically what I'm saying is like, so you have the z, you have the x, the y, and whatever, can have anything here, but it doesn't matter. But you are creating an indicator function, which is a function of x. Right, so it's a function of x, so the direction is to here. And this indication, that's a new node, it's independent of what I'm asking here is the indicator function. If the indicator function, oh, now I'm here. I'm here. So it's conditional on x and z. And if the y and the y and the indicator function are independent, I can put this as together, right? So this multiplication becomes this, not this, but with the x, only if y and the indicator function are independent. And you can see this from the graph. So the y is independent of y given x. So I'm conditioning on x here. Then I'm also conditioning on z, so that's fine. And so okay, and then there is a step here that the x. So basically, I'm just skipping one step. But once these two together are these two are together in the expectation, I can remove the x again, because since I'm getting just, so now it's the product between the y and this indicator. So the indicator is going to be 0 if the x is not equal to x. So conditioning on x is irrelevant, so I can remove again. So this part here, it's kind of tricky to show from here to here, depends on this steps here. In the counterfactual language, it's a little bit easier because you automatically have that the y-x is independent of the indicator function, and this is going to be the counterfactor here. But anyways, this is going to be true. And now this is just a function of z, and when it's a function of z, you can put inside of the expectation. So now from here to here, I'm just putting it inside. And then using the iterated expectation, I can remove the expectation of z and then just get the expectation here. I mean, it's just a curiosity if you like the proofs, but you can show that if you kind of use the weights, in the end it's nothing. So the weight is still here, right? So without using the weight, you are just getting the expectations of the y's that have equals x equals to x. So anyways, this is the proof. Yeah. And okay, so there's no much in the literature about the estimation of the front door, but I wanted to show because it's not that hard. I mean, it's hard, but since people don't really know about the front door because they are in the front, in the back door, I mean, they are in the ignorability condition, the condition ignorability condition, they don't really have, there's not much research about estimation in other formulas. So to estimate the front door, people kind of started already, so there are some recent results. And it's not that hard because front door is basically a composition of two back doors. But in the end, you still have to estimate some densities and kind of apply Monte Carlo approach. So for example, this is so imagine that you have a set M that satisfies the front door. Then this is going to be the estimate to estimate. And we can compute the average causal effect in this following way. So basically, I want to apply the expectation using this probability distribution. So here are the steps. Let me go through it. It's not that hard. So I applied here, so that in parentheses just a copy of the distribution. Then I can move the sum over M. It was here. Now it's before the y, so I put it in the beginning. So this again can be done due to Fubini theorem. then these two are actually, what I'm doing is moving the sum over y and y to be close to the probability of y given m and x. So I'm moving this sum to be here. That's what I'm doing. The other part is the same. And now between parentheses, it's again the conditional expectation of x. Sorry, it's the conditional expectation of y given m and x prime. That's the definition of conditional expectation. So that's what I'm doing here. And since this is a function of just x prime, because m is fixed, so this is a sum over m, so when I compute this, m is fixed. So this sum here is just a sum over one particular m, and this is a function of just x. So this is actually the expectation over x of this function. And in the end, I still have this probability to estimate. So because of this probability, we don't have like an easy way to estimate just through regression. However, okay, I'm just putting here why the things happen. But we can kind of have this, use the law of the large numbers again, and use kind of a Monte Carlo approach to estimate this expectation, as long as we are using values of m that are following from this distribution, right? So that's basically what I need to do. So given this expression, we can, by Monte Carlo, we can compute the value, the expectation of this thing here. You just look at this as a function. So we can compute this by using Monte Carlo, as long as the values, so this is going to be a function of m for a particular x, of course, but as long as the m's are representative of this distribution, I can kind of just apply these m's and compute this expectation and just average over all these values, and then this is going to work. This is the principle by Monte Carlo. Like, if this was just a probability distribution of x, for example, maybe you know it. Like, for example, if you have, so how in Monte Carlo you do this, right? So we can get a function of x, probability of x. So this is just a function. So if I can, so I can compute this easily by any function, by sample x's following this distribution, and then applying here, and then this is just the, so that's, sorry, this should be the, so if I have a large n, this is going to be the expectation of fx. So this maybe you know. However, what I have there is a different probability and a weird function. But I can't compute that weird function. We can just separate this as a problem. And as long as I can sample, and this probability has to be the probability of the arguments of this function. And you can see there that this is exactly what's happening. It's like I only need the m, as long as the m is the m's for this particular x of my intervention. Once I have the m, the other part is fixed, is like separated, is independent. Like, that's just a sum for all values of x, but the m is a parameter that it should be given. So as long as I'm getting samples following this distribution, I can compute this expectation by just applying many times this function and just get the average. So that's what I'm doing. So first I need a way to estimate this, and this can be hard, but anyways, that's the hardest part. We can use a density estimator here. So we have samples for x and for m. So we just need a way to sample m's for from a given x. So as long as you can, in m can be high dimensional as well. So you need like a density estimator that's multivariate, like for multivariate density estimations, density estimation procedure. But once you have this, then in separate, you also have samples for X, Y, and M. So you can't compute using regression or machine learning, but it's just a function that receives M and an X. This is actually the so that's just an expectation of M, of Y given M and X. And this is just for the intern part here. And then we will have to average over X. But that's what I'm saying here. We need to average over X as we did in the backdoor. But here are the procedure, is exactly the steps. So first, we randomly draw samples. So X is fixed, it's coming from this. So if we have a generator of samples, you just ask, give me n samples of M for this particular X. And it was trained by using M and X. So I can get like any sample, n samples of M. Then using this estimator here, you just compute what would be the predicted value of Y for this particular M that you sampled and the original X. Then you need to now get the average over all values, because now you need to consider basically it's doing the sum twice here. So basically this expectation of over X and the expectation of over M. So there are two expectations you are doing together because you are varying the X's here. So you have a sample of X's and a sample of the M's. So kind of when you get the average of all these predicted values, you get the expectation of all of them. So you see, it's not trivial. Like this is kind of okay-ish. Like it's not that it's not a monster. It's just computing one estimation, then we just need to estimate one density and then one expectation. But anyways, we will have here all the issues of the backdoor approach, and there is the additional step of finding a way to generate samples from M to actually feed to this estimation, to this function here. But you can do it. Okay, so that's it. I almost done. So before finishing it, I want to just give you a flavor what's still what I couldn't cover. So what's still that you can maybe be interested in. So that's the entire workflow. I don't know if I showed this before. No. So basically we start. Oh, sorry. So basically we start with the SCM. So the SCM is what kind of explains everything, but it's an unobserved nature. So we have here, and no one wants to, I mean, you could directly solve the causal problem by trying to estimate a structure causal model. You have like a structure equation modeling that tries to do that, but you need to know a lot about the environment to actually know the parametric form and maybe make sure that the assumptions behind it, like the distributions of the arrows, the independence of the arrow terms, everything is actually holding. So in causal inference, in the causal inference field, we give up. We don't want to do this. But we kind of understand that there are a lot of things that are induced by the SCM. So the first thing is the data, right? So any data that you can that you have here, it's going to be used. That's the observational distribution. And the A part is called statistical learning because it's what people have been done for many years, and it's just about getting data and estimate distribution. So for example, this lecture, in the end of this lecture about estimation, it's in this part here. So how can you compute conditional probabilities, expectations, and so on. Also from this distribution, we can get some idea about the causal structure. So here it's called causal hypothesis, but you don't need actually to get the causal diagram itself. You can get like the equivalence class or something so there are several works that instead of getting a peg, you just get like the order of the variables. So for example, causal discovery for film ordering, partial ordering, so this exists as well. But one thing that's in this B that's called causal learning is how can you extract from data and also sometimes combining prior knowledge. So the FCI combining prior knowledge, there are some very recent works that are showing it is still not a complete algorithm, but there are ways to combine knowledge that's available with the data and get a refined version of the structure of the model. But basically this process of combining data and knowledge, and this data can be interventional data, can be observational data, or data from multiple studies and data sets. So there are several extensions that we couldn't see, but basically it's in this step that's called causal discovery or causal learning. And once you put together in a very transparent way, this is going to be our causal assumptions or causal constraints. That's going to be an input of causal identification procedures. And this is what we call causal inference itself, because basically you are combining data, so data that was here, with also the structure to get identification results. And this can be for counterfactuals, can be for interventional distribution, can be for anything. So those are queries. And we only saw cases that the answer was either positive or negative. But there are studies where you have actually partial identification, so we couldn't cover this here. But it's basically how can I get an interval of confidence? So I don't have like a point identification, but I could get like, I don't know, but it's between 0.1 and 0.7, doesn't include the 0. Maybe this is enough for me. And there are works for this. And if the answer is positive, there is still this new phase that's called causal experimental design causal experimental design is in this side here. So if the answer is no, you could, for example, design new experiments to either collect more data or do certain so you can define which variables are the optimal ones to do an intervention, so that in the next iteration you know what's the causal diagram, so that, or parts of the causal diagram that allows you to have the identifiability. So it's an optimal experimental design. So if you have a no answer, you are not doomed. You're just, you can go through these experimental designs and just, if you have access to data or if you are able to perform an example, maybe you can go back and do a next iteration. And if you are lucky and you got the answer, you actually can also go back in the loop by considering this as a new knowledge. So this could be for like you can use this type of information to help other studies where you would now answer different questions and so on. So in blue are the only things where we kind of, we are focused on this blue part and we didn't cover everything. So there's like a huge world out there. And I listed here a lot of topics, just a list. As I said, there's no references, but if you are interested in any topic, just send me an email. I'm happy to send you the papers. So for example, extensions to cyclic systems that exist. So the PEG actually covers some cycles, although we just saw acyclic systems. It can be shown that the same FCI algorithm under like something that's called sigma separation, not this separation, it's actually covering dependencies and independencies in cyclic systems, but it's not complete. But it's a really nice extension, like there are a lot of people working in this direction because the systems can actually have feedback. Instead of working only with only one data set, as we saw here, we could have like multiple data sets, and these data sets can cover not only from multiple centers, but can be like under different experimental designs. So ones can be observationals, other can be experimental. There's something called soft intervention. So we only saw here one type of intervention, that's the do operation, which is called hard intervention. So basically you transform the x variable into a small value x. So it's like a definite change. And the soft intervention is like you just have a probability to change the x. So sometimes you change not the equation of x to just one x, but the small x, but you change it to another different function. And this can be receiving new parents, maybe removing some parents, or can actually add a new probability for the variable. And you have like extensions regarding, like, for example, sigma calculus for soft interventions, and I mean everything related, like ID algorithm for soft interventions. So that's another. So the gap between, so this is something that a PhD student could do. So I know the guy that created the soft calculus, the calculus for soft interventions. I mean, I cannot say that he is not amazing. He is really amazing, but he spent like several years in his PhD, and he could solve it. So the knowledge that he had when he developed it is the knowledge that you have now. So what I'm saying is, like, the gap between what is done and what can be done, it's small. So, and you can do a lot by just knowing what you know already. And you can now, with your knowledge, read their papers and understand what soft intervention without many issues. Extension to time series data is not that hard as well. You just need to know to make some assumptions between like regarding the process. So if you know time series analysis, we still have here to assume stationarity. So basically you have a sliding window, and the graph is going to be for this specific window where this is going to be, like, you need to find the gap. So there are techniques to find, like, basically every variable depends on some points in the past, but this is fixed. This window is fixed. Like, you cannot recover the process for the entire history as like a different graph or different arrows for different times in the point. You basically assume stationarity, and then you learn the graph over a window, and then this is assumed to be like invariant across time. But this can be done. As I said, there's like a lot of work about including background knowledge in the FCI algorithm. There's a recent paper, I really like to learn more about it, but it's still not complete, but it's going to a very interesting direction. There's something so there is a way to rewrite all the rules of this FCI into logical statements related to ancestral and non-ancestral relationships. So you can also rewrite the FCI algorithm as an optimization problem, and then instead of getting one solution, you can get, like, sometimes you don't have solution because of conflicts due to unfaithfulness. So instead of looking for the solution, you can get just the optimal, the one that it has less conflicts or something like this, and also allows to include background knowledge. So it's a really nice characterization of the FCI algorithm. I've been working a lot in increasing robustness to violations of faithfulness. There's a lot of literature related to this, but you see that there's a lot going on. But everything is localized. Like, the hard part about the FCI algorithm, you know. So these are just small extensions, and you could all go home and learn by yourself. But I'm happy, like, if you are interested, we can read together these papers next semester or something like this. More on causal identification. So I couldn't cover linear systems. They are so nice, so easy. And I could cover, but I mean, I'm already over time. And but basically in linear system, everything works. Like, you have, like, instead of like the back door gets you, you have like a single door criterion instead of also the single door criterion allows you to identify the coefficient of the edge, and you can apply several tricks to get, like, for example, in a path, in a chain. So for example, the x and y here. So the covariance between x and y is just the effect of this path plus this other path. So it's just the sum of all the paths. So if you condition in a regression x, this is the outcome and these two are the predictors. The coefficient of x in this regression is a coefficient related to this edge. So it's just the regression coefficient is the causal effect. So things are really interesting in linear systems. So if you are willing to assume linearity, most of the estimation procedures reduce to just do regression. And even counterfactuals, if every counterfactual quantity is identifiable as long as the interventional quantity is identifiable. So in many cases, we could just assume linearity and then you get identifiability. Also, we didn't cover a lot of criteria to allow you to identify if a quantity is non-identifiable. So there's like something related to heads and that I couldn't cover. Anyways, this is more, I don't feel that this is more like theoretical. It's good for theoretical reasons, but for applications you don't really need. If you have an algorithm, but in the end you can prove that every time that the ideal algorithm fails, you have a hedge, it's a structure in the graph, so it's just a connection. Generalized effect identification. So sometimes you don't have, you have like experimental data available. So if you're interested in the effect of X on Y, so you sometimes have data from like other experiments. We call it surrogate experiments. So you have data, for example, in the variable W plus the observational distribution. So how can you combine all these distributions to maybe help you to get identifiability? Here is about the soft interventions, partial identification, I told you as well. Another thing that's really popular is called effective transportability. So if you have like experimental study and you got the effect of X on Y through experiment, you only guarantee internal validity, which means that the effect is that effect for the population that you got in the sample. But if you transport this to another country or to another animal, like you did the experiments in rats, is this going to work in humans? You would need to transport it. And to transport it, you need many, many more assumptions. So this explains how and in what conditions you can do it. Other topics. So there is also a connection with deep neural networks that kind of helps to get identifiability and estimation at the same time. It's still in the beginning. Basically, the idea of this is kind of you have a optimization procedure internally. So if you try to estimate so basically you can manipulate. So first of all, you can do inductive bias by learn a model that follows a causal graph. So you don't do just one deep neural network as it is. You have to enforce the order of a causal diagram, and the effect can be computed by the manipulated graph. So you have like a parallel between what would be the effect in the observational model and in the interventional model, and you kind of estimate. So you force that those are the same, and then in the end you get an estimate of the probability of y given x or something like this, but in the interventional model. And if the value is then you can kind of there are two optimization procedures here. So you can either minimize this the effect of the x on y, and also maximize the effect of x on y. And if they match, it's because like for every model where you have like your focus is to estimate the effect of x on y. So you can kind of for every model that fits a causal diagram, if the maximum one is the same as the minimum one, is because for all models they are the same. So the idea is exactly that. So you reinforce that the model follows the structure, and then you compute, you maximize the effect in the sense that you get the model where you get the maximum effect, and then you minimize, again, you have a new training of the deep neural network to minimize the effect of the same effect of X on Y. And if they are really close, they kind of say, okay, it doesn't matter what's the model that's fitting, they're going to always have the same effect. Then we have identifiability and the effect with that one. You don't even need a formula or anything. Anyways, this is still like ongoing, like the guy that's working on this is also a student. He did this for assuming that you know a causal diagram, so there's no works for pegs yet, but you can do effect of interventional distributions, and recently he published for counterfactual distributions. But the idea is not that hard. It's basically checking what's the maximum and the minimum of one particular effect for all possible models that you can fit with a neural network following a causal diagram. But it's interesting. Counterfactual identification, as I said, there are several axioms, identification algorithms. I just touched the surface here. But one thing that's really useful with counterfactual is to do mediation analysis. Maybe you have heard about it. So basically, I want to know what's the direct effect. So sometimes you have a total effect. I can get the contribution of the effect through some specific paths in the graph. So if I have like several paths connecting X and Y, so I can get the probability of Y given X. This is easy. You don't even need the probability given M1 and M2, but sometimes I want to know what's the effect just through this path here. So it's called path-specific effect, or to this other path. And this is really useful, especially for fairness, because sometimes you want to know what's the contribution of the effect, for example, through some variable that's, I don't know, sex or gender or like age or race or something like this. And you can evaluate how much of the effect is because of this protected variables, they call. As I said as well, there's so much more about estimation on the backdoor adjustment. Like you have a variety of frameworks leveraging machine learning, like it's combining all this stuff that I mentioned. And there's something called doubly robustness that combines regression, because another limitation of regression is that you need, if you're not using machine learning, you need to assume that you got the correct parameterization for it. And doubly robust means that you can fail. So basically there are two assumptions, and you can be correct only about one. So you cannot be incorrect about both, but if you are correct just about one, this is still fine. So it's robust for misspecifications. There's like this idea of checking balancing that I also couldn't cover. And also a lot of things about optimal causal experimental design, and the causal reinforcement learning is also a way to combine reinforcement learning with the causal diagram. So how can you find in our online reinforcement learning strategy which variable I should either like where I should perform the intervention, or like, because there's like exploitation and exploration, right? So in the exploration, you just evaluate the scenario where you kind of learn more about the environment and construct a causal diagram. And in the exploitation, I guess, you need to find which intervention you should do. And you can use causal experimental design to find where you would intervene now. Because in the usual reinforcement learning approach, you kind of just this in a random way. You can leverage the causal diagram to know what's the best intervention that you can do. Anyways, there's a lot of things that I found personally all interesting, so I would be happy to talk more, or if you, anyways, or if you ask me, I can give you some pointers. But that's it. I really hope that you enjoy all this journey, and good luck on your future endeavors. But yeah, that's all from here.